In February of 2026, a team of scientists published research that finally solved a mystery Voyager 2 had been quietly carrying inside its own data for 39 years. And that wasn't even the first time this particular spacecraft had handed researchers something they genuinely couldn't explain. Nearly a decade earlier, when Voyager 2 crossed the true boundary of our solar system, it recorded a magnetic field pointing in a direction that violated almost everything scientists expected to find there, a puzzle that remains only partially resolved even now. Two separate decades-apart discoveries, both genuinely shocking to the researchers who uncovered them, both traced back to a single, nearly 50-year-old spacecraft that keeps finding new ways to upend what we thought we understood. This is the real story of what Voyager 2 has actually discovered, using nothing but published, peer-reviewed research, and I promise you, the true version of these events needs no exaggeration to earn the word shocking. Let's start with the older of these two mysteries, because it sets up everything that follows. On January 24th, 1986, Voyager 2 became the first, and to this day, the only spacecraft ever to fly past Uranus, coming within about 81,000 kilometers of the planet's cloud tops during a flyby that lasted only a matter of hours. In that brief window, it gathered essentially all the direct, close-up data humanity has ever collected about that planet, discovering 11 new moons, 2 new rings, and measuring a magnetic field so strange, tilted 59 degrees from the planet's own rotational axis, that it trailed a corkscrew-shaped magnetic tail stretching some 10 million kilometers behind the planet into space. And buried within all of that data was something that immediately struck the scientists monitoring it as deeply strange, a reading of Uranus's radiation belts showing far more electron radiation than anyone thought should be physically possible for a planet like that. For the next 39 years, that measurement just sat there, unexplained, not disputed, not dismissed, simply unresolved, a quiet asterisk in planetary science that got mentioned in textbooks with a shrug attached to it. Nobody had a second data set to compare it against, because nobody had ever gone back. There was no way to know whether what Voyager 2 recorded reflected some strange permanent baseline feature of Uranus, or whether the spacecraft had simply arrived at an unlucky moment, catching the planet in the middle of some temporary, unusual event that happened to be unfolding during the exact few hours it flew past. That question finally got an answer in February of 2026, when a team at the Southwest Research Institute published new findings based on an entirely different approach than anything tried before. Rather than trying to explain Uranus using only data from Uranus, researchers turned to a much more familiar, much better understood source, Earth. Over the decades since Voyager 2's flyby, scientists have built up an enormous, detailed body of knowledge about how our own planet's radiation belts behave, particularly during a specific kind of solar disturbance called a co-rotating interaction region, a disturbance that forms when faster streams of solar wind catch up to and slam into slower streams ahead of them, compressing the material between them into a dense, turbulent structure that can dramatically supercharge a planet's radiation belts when it sweeps past. The research team, led by Dr. Robert Allen, took everything scientists have since learned about these events here at Earth and used it as a lens to re-examine exactly what Voyager 2 actually flew through on that January day in 1986. What they found was that the spacecraft had very likely arrived at Uranus in the middle of exactly this kind of event. And here's the detail that makes this genuinely surprising rather than simply confirming what everyone already suspected. For decades, the working assumption had been that the intense high-frequency plasma waves detected during the flyby, the strongest ever recorded during the entire Voyager 2 mission, would have scattered energetic electrons and caused them to fall harmlessly into Uranus's atmosphere, essentially draining the radiation belts rather than filling them up. But newer research, built from direct observations of a strikingly similar event that actually happened at Earth in 2019, has shown that under the right conditions, those same kinds of waves can do the exact opposite. Instead of scattering electrons away, they can accelerate them, injecting even more energy into the belts, and making them considerably more intense than anyone had originally modeled. That 2019 event at Earth became the missing piece researchers needed. It gave Dr. Allen's team a direct, present-day comparison to test their theory against, and when they ran the numbers, the match was compelling. Voyager 2 hadn't stumbled onto some permanent baseline feature of Uranus at all. It very likely flew directly through a rare, violent burst of space weather, a cosmic storm arriving at almost exactly the wrong, or depending on how you look at it, exactly the right moment to be captured by a passing spacecraft that would only ever fly past that planet once. Sit with that for a second, because it's genuinely worth appreciating just how much this quietly reshapes nearly 4 decades of assumptions. Humanity has had exactly one close look at Uranus in the entire history of spaceflight. One flyby. A handful of hours out of a mission that has now run for nearly 50 years. And there's a real, credible chance that during that narrow window, We happened to catch the planet in the middle of an unusual intense event that isn't actually representative of what Uranus typically looks like the rest of the time. Everything scientists have built their understanding of that planet's radiation environment on for the better part of 4 decades may have been based on data captured during conditions that were, in a very real sense, not normal at all. Dr. Sarah Vines, a colleague of Dr. Allen's on the research team, pointed directly at that 2019 Earth event as the key that finally unlocked the puzzle, explaining that if a similar mechanism was interacting with the Uranian system back in 1986, it would explain exactly why Voyager 2 recorded all that unexpected additional energy in the first place. This discovery carries real, practical weight too, not just historical curiosity. NASA has increasingly discussed sending a dedicated orbiter mission back to Uranus, something that hasn't happened in the nearly 40 years since Voyager 2's brief flyby, and the National Academies of Sciences actually named exactly this kind of mission its top priority for large-scale planetary science in a major decadal survey released a few years back. Engineers designing that future spacecraft need an accurate understanding of what kind of radiation environment it would actually have to survive out there for months or years at a time, not just a few hours. If the numbers Voyager 2 recorded represent a rare, temporary storm rather than a stable, everyday baseline that changes the entire radiation shielding conversation for any future mission, potentially the difference between a spacecraft that survives its full planned lifespan and one that doesn't. Now, let's move to the second genuinely shocking discovery, one that happened years earlier, but remains, in some ways, even less resolved than the Uranus mystery. In November of 2018, Voyager 2 crossed the heliopause, the true boundary separating our entire solar system from the wider galaxy beyond it, becoming only the second human-made object in history to leave the protective bubble of the sun's influence entirely, following its twin, Voyager 1, which had made the same crossing 6 years earlier, in 2012. And almost immediately, its magnetometer recorded something that directly contradicted decades of prior expectation. The magnetic field just outside that boundary, in the supposedly separate foreign territory of interstellar space, was pointing in almost exactly the same direction as the magnetic field back home, inside the heliosphere. Scientists had actually caught a hint of this same strange alignment years earlier, when Voyager 1 made its own crossing in 2012. But with only one spacecraft's data available at the time, researchers genuinely couldn't tell whether that alignment reflected some real physical property of the boundary itself, or whether it was simply an unusual coincidence specific to wherever Voyager 1 happened to cross. Voyager 2's own readings, gathered 6 years later at a completely different location along the heliopause, settled that uncertainty. The two datasets agreed. The magnetic fields on both sides of the boundary really do appear to line up, and that alignment isn't some one-off fluke tied to a single spacecraft's specific crossing point. Why does that matter so much? Because it directly contradicts the intuitive picture nearly everyone, including most scientists working in this field, had assumed for decades. If our solar system's magnetic field and the wider galaxy's interstellar magnetic field come from entirely separate sources, shaped by entirely different physical processes, there's no obvious reason they should line up this precisely, especially not right at the exact boundary where one supposedly gives way to the other. Researchers studying this data have been genuinely candid about how unresolved this specific puzzle remains, even years later. Space physicist Merav Ofer at Boston University, who has spent years studying this exact question, has described the situation honestly, admitting that scientists now know how little they actually understand about the heliosphere, calling it far more complex and far more dynamic than anyone had previously assumed. This wasn't the only surprise buried in Voyager 2's interstellar crossing data either. In November of 2019, 5 separate papers, each covering findings from one of Voyager 2's still functioning instruments at the time, were published together in the peer-reviewed journal Nature Astronomy, painting the most detailed combined picture yet assembled of conditions right at the edge of our solar system. Researchers confirmed something they had actually predicted correctly, that interstellar plasma is considerably denser and noticeably colder than the plasma found inside the heliosphere. But they also found that the actual transition between the two environments was remarkably sharp and clearly defined, closer to a genuine physical wall than the slow, gradual blending many scientists had originally expected. That sharpness led researchers to propose that the heliosphere's overall shape likely resembles something like a blunt, rounded bullet, rather than the smooth, simple sphere many earlier, simplified models had assumed. Then, in October of 2020, came yet another layer to this same story. Astronomers reported a significant, genuinely unexpected increase in plasma density detected independently by both Voyager spacecraft, despite the two probes having crossed into interstellar space at completely different locations, separated by 6 years. That shared, unexpected density increase suggested this wasn't simply a local, isolated quirk tied to wherever each individual spacecraft happened to cross the boundary. It appeared to be a genuine large-scale feature stretching across a meaningful portion of the actual space surrounding our solar system, reshaping how researchers think about the true structure of our cosmic neighborhood. There's a real, practical dimension to all of this, too, one connected directly to questions of safety and survival. The heliosphere functions as a genuine physical shield, deflecting more than 70% of the dangerous, high-energy galactic cosmic radiation that would otherwise reach the inner solar system, including Earth itself, protecting every living thing on this planet for the entire history of life here, almost entirely without anyone noticing. Understanding exactly how that shield behaves, how thick it is, how reliably it holds up under different conditions, carries genuine weight for any future planning around long-duration human spaceflight beyond our solar system's protective bubble. And that understanding is only possible because two aging spacecraft happened to be equipped with working instruments at exactly the moment they crossed this critical boundary. Both of these stories, the Uranus radiation mystery finally solved in 2026, and the magnetic field puzzle still only partially understood years after Voyager 2's 2018 crossing, share something important in common. Neither discovery came from a dramatic, single moment of realization. Both required years, in the Uranus case nearly 4 decades, of patient, careful comparison against newer data, newer models, and newer events observed elsewhere before scientists could actually make sense of what this aging spacecraft had already shown them. Voyager 2 didn't need to transmit anything new to teach us something genuinely surprising in either case. It had already told us. The rest of science simply needed time to catch up to what the data was actually saying. So here's what I actually want you to take away from all of this. Voyager 2 is currently more than 13 billion miles from Earth, running on a dwindling supply of power with its instruments being I deliberately shut down one by one to stretch the mission as far into the future as physics will allow. And even now, decades after its last close encounter with a planet, it continues teaching us things, not always through new transmissions, but sometimes through old ones that simply took the rest of the scientific community years to properly understand. A magnetic field that shouldn't line up the way it does. A radiation reading that sat unexplained for 39 years before finally making sense. If a single flyby's worth of decades-old data can still quietly rewrite entire chapters of planetary science, it raises an honest, open question about what else might still be sitting in the spacecraft's records, waiting patiently for the rest of us to finally catch up. If you want to know what scientists eventually determine about that unresolved magnetic field alignment, subscribe and turn on notifications, because that question remains genuinely open, and researchers are actively working on it right now using data these two aging spacecraft continue sending home. And drop a comment telling me which of Voyager 2's discoveries you found more genuinely surprising, the 39-year-old Uranus mystery finally solved, or the still unexplained magnetic alignment at the edge of our solar system. Because honestly, after working through both of these stories, I don't think either one has fully finished surprising us yet.